Hi, this is Ryan Izard here for Clemson University's Electrical and Computer Engineering Department. This is the first of a series of videos for the ECE 273 lab, Assembly Language Programming, and today we're going to go into Lab 1, which is an Introduction to Assembly. So, let's start by asking the question, what is assembly language? To answer this, let's consider a somewhat familiar program written in C, Hello World. C, and other languages of the like, are very high-level languages. In order to convert C code into code that's understood by the computer, we typically invoke a program called GCC, which is the GNU compiler collection. We use this on a Linux machine, and we can give it our C file here, and GCC works some magic, and it spits out a file typically named a.out if we don't specify otherwise. This is our executable program, and this is what actually runs on the computer. However, GCC is actually hiding something from us. Before it gives us this executable program, it actually converts our high-level C code into what's called assembly language, which is shown here. Now, I don't expect you guys to understand what this code is actually doing here, and in fact, we're not going to go into much of what you see on the screen. This course is only an introduction to assembly language. However, what you should get out of this is that high-level languages like C are not understood directly by the computer. They must first be converted into a language that the computer can understand. Assembly language, as shown here, consists of very basic instructions that are designed to do specific tasks on the hardware of the computer. So, for example, you can see here there's an instruction move, which, as you could guess, probably moves some data from one part of the computer to another. There's another instruction here called call, and that most likely calls a function. These instructions and the many others that we'll go over the course of the semester are directly mapped to the machine language of the computer. This machine language is what is actually understood by the processor. So when you write code in assembly language, you're essentially writing instructions that the processor can directly interpret. So, for example, as we showed before, the processor can understand how to move data, it can understand how to call different labels or functions, it can understand how to do basic mathematical instructions. However, it cannot understand, and it does not understand, how to do things like printf, how to print something to the screen. We must first convert high-level languages like this into very specific instructions that the processor can understand. Okay, so let's take a look at assembly language from a hardware point of view. Whenever we execute our programs, they are loaded from the hard drive into main memory, or RAM. Assembly instructions allow us to move data from RAM, to and from RAM, into the CPU. The CPU is what actually executes the instructions that are present in the program. In order for it to do this, the CPU has something called the ALU, the Arithmetic Logic Unit. This is what performs the mathematical instructions such as add, subtract, multiply, divide, or anything of the like. Also present on the CPU are things called registers. Registers are data storage elements on the computer that you can store data in for very quick and easy access. As we know, it takes more time to actually go out into RAM and retrieve some data, so the CPU contains some storage elements for rapid data access. Whenever we execute assembly instructions, they either involve moving data to or from RAM in the CPU, or they involve performing mathematical instructions on the CPU using the ALU. For example, we could have an instruction that says move data from some place in RAM to the CPU, and then we could have another instruction after that that says do something with that data. For example, we could have an instruction that says add that data from that we've just saved in the CPU to another piece of data that we have in the CPU. It's the small blocks like this, the small building blocks like these instructions that assembly consists of, that allow us to build larger and more complex programs that we're used to writing in C and other high-level languages. However, the beauty behind high-level languages is that it masks this whole process from us. We don't have to worry about moving data from RAM to the CPU and back and forth, and we don't have to worry about performing the very specific computations within the CPU. These are all handled by high-level languages, which is great for programmers since it allows us to more efficiently and quickly write and debug our programs. However, what high-level languages also do is they mask how the computer actually works. So in order for us to gain a good understanding of what actually is going on in the computer when we write some programs, we need to really understand and learn assembly language. Our next question would be then, why do we care to learn assembly language? If everything has been done for us already such that we can use high-level languages to write our programs, why do we care to learn assembly? Well, like we've alluded to earlier, learning assembly language gives us a much greater understanding of how the computer actually works. Not only does it do this, but learning assembly language can also give us insight into how a compiler works. What if you one day wanted to write a new version of GCC or some other compiler? You would need to know assembly language in order to do that, because what the compiler is doing is it's taking your high-level code, it's converting it to assembly language, which is dependent on the hardware of the computer, and that way your program can actually be run by this processor on the computer. So if you wanted to go into the compiler business one day, you need to learn how to use assembly language. Similarly, if you wanted to work in computer hardware, and maybe you want to come up with the latest and greatest CPU that's going to completely change the way we do computing, you're going to need to come up with some sort of instruction set architecture that'll have a corresponding assembly language so that high-level programs can be mapped to your new processor. So learning assembly language has a lot of great benefits, and not only can it do what we've talked about already, but learning assembly language can also make you a much better high-level language programmer. Now, what do I mean by this? How can this be so? If you actually understand how your programs are being implemented in the hardware of the computer, you can more easily write very efficient code, and this can also help you to debug your code much more easily. So assembly definitely has its benefits. And if I haven't convinced you so far of why you should learn assembly language, if anything, it'll give you an appreciation of what's been done for us already. Back when computers were first developed, all they had was assembly language to program in. Now, using assembly language, we've created things like compilers, which has allowed us to have nice fancy operating systems and higher level languages, so we don't have to worry about this so much anymore. In essence, assembly language is somewhat of a lost art, unless you go into some of the businesses that we've already discussed, but it should give you a really good appreciation for the high-level languages that we use. So now let's talk about what we're going to learn over the course of the semester. As I stated earlier, this course is designed to be a basic introduction to assembly language. So for Lab 1, which is what we're talking about today, I gave a basic overview of what assembly language is and how it works on the computer, and also why we want to learn it. Lab 2, we're going to talk about the basic mathematical instructions that we can use in the CPU, such as add, subtract, multiply, and divide, and also moving data to and from the CPU from memory. Lab 3, we're going to talk about program flow control, which is how to move from one location in your program to another. As we know in C, we have, in other high-level languages, we have control statements such as for loops, which allow us to execute a certain block of code repeatedly, or maybe we have while loops to do the same thing. Or we also have the dreaded go-to statement, which allows us to jump from one point in the program to another point. We're going to learn in Lab 3 how to implement these types of flow controls in assembly language. In Lab 4, we're going to talk about the different addressing modes that we have in assembly language. These addressing modes allow us to work with data types such as arrays and pointers in assembly language. In Lab 5, we're going to talk about subroutines in the stack. Subroutines is just a fancy word for functions. We're going to learn how we write functions in assembly language and how they're actually executed in the hardware of the computer. In Lab 6, we're going to take Lab 5 to the next level and learn how to write functions or subroutines that take arguments and return values. So, for Lab 1, we're going to just discuss the basics of how we are going to do the rest of the labs over the course of this semester. As I mentioned, assembly language is specific to the hardware of the computer. Now, the assembly language we're going to learn in this class is x86 assembly language. x86 assembly language is an assembly language that was based on the Intel x86 version of processors. So back in the day when Intel first came out with CPUs, they started with the 8088 and 8086, and these were the first CPUs to have an instruction set which is now referred to as the x86 instruction set. Since then, there have been many CPUs created by not only Intel but other manufacturers like AMD. All these CPUs that are termed x86, they all understand a common assembly language. And this is the assembly language that we're going to learn in this course. Having said this, x86 assembly language is a 32-bit language, meaning that each instruction in assembly language, so for example, what we saw previously, we saw there was the move instruction, which we'll talk about in Lab 2. Each instruction takes up 32 bits, or 4 bytes in the computer. So if you noticed, many of the CPUs or operating systems nowadays are termed x86_64. These are processors that can understand the x86 assembly language. However, it's a 64-bit language, meaning that the instructions are 64 bits in length. Now, there is more than one version of the x86 assembly language. We have the Intel version, and we also have the AT&T version. The only difference between these two is the syntax. As we'll learn over the course of the semester, assembly language instructions commonly take two arguments, or two parameters, known as the source and the destination. Intel instructions have the destination followed by the source as the arguments. However, AT&T syntax assembly instructions have the source followed by the destination. There's no pros or cons to one form or the other. However, we're going to use AT&T because that is what GCC understands. So over the course of the semester, although we will be programming an x86 which is designed to run on Intel or other like CPUs, we are going to be using the AT&T syntax because that is what GCC understands. Now, over the course of the semester, for each lab, we're going to have two files. One is going to be called our driver file, and this is going to be a C file. And another file that we're going to have is going to be our assembly file. And this is going to be a .s file. As we know from C, any file that we make that has C code in it, we either name it or give it an extension .c for our C code or .h maybe for a header file. Assembly files will always take the .s file name after it, the .s extension. This tells GCC that when it looks at this file that it's going to be an assembly file. Now, all the programming that we're going to do is going to be directly in this assembly file. However, we're also going to have a C file that goes along with our programs. Because this is an introductory assembly course, we aren't going to go into the details of how to actually write an assembly program from the bottom up so that it can be executed. We're going to instead use what we call a driver file in C. You can look at this file and basically it's going to consist of a main function and some other code that's going to call our assembly file and use it and run our assembly code. So for example, if we're not actually going to do this, but say we made our own printf function and we're calling our own printf function within the driver, our version of printf would be implemented in our assembly file. It's important that we do not modify these driver files. They've been written for us already, and we can see them in the lab manual. These programs are designed to call our assembly code and run it from within the .s file. And as stated in the lab manual, for all of our labs, our S file will be partially completed for us. If you look in the back of each lab in the manual, we have a few files. We have the driver file that's given to us, which we need to copy and paste or type that out manually and create our C driver file. We have an assembly stub. Now this is what we're going to use to actually implement our assembly program in. What do we want to write in assembly? For each lab, we're going to be given a C specification code file. We don't actually want to run this program, and in fact, if we tried, it wouldn't actually run. It's just pseudocode. What we want to do is look at that specification file and implement the logic in it in assembly language. So for example, once we get to Lab 2, we'll be given a specification file. We want to translate that code into assembly language. into the and put that in the assembly stub file, which is the .s file. That is what we're going to actually end up running. So let's go through that one more time quick to make sure everybody's on the same page. We have our C file, we have our assembly file, both .c and .s. This file is going to have a blank in it, and this is where we're going to write our assembly code, and this is going to be called a stub. So the assembly stub, it's been completed for us, but it's going to have some parts that are incomplete. And these parts that are incomplete, that's what we're going to want to implement in assembly language. Where do we base this code from? This is from another file, which is our specification file. We base our assembly code here on this specification file. So the specification file is going to be some C code. We want to translate this into assembly and put it in this assembly stub. So once we have done this, we need to save both of these files in the same folder. Now, where you save them, it doesn't matter. Just make sure they're in the same folder. Once they're in the same folder and you have them saved, we're going to compile these two files together using GCC. The way we do that is We do that, using GCC. We're going to use a special command you probably haven't seen before, -M32. M32 says that the assembly code we're writing is 32-bit assembly code. Recall that on the previous slide, the previous 2 slides ago, we talked about we had x86 and x86_64. Most processors nowadays are x86 64 processors because most computers are now 64-bit. However, the code we're going to be running is 32-bit, so we need to tell GCC that to look for 32-bit code. That's what the -M32 flag says. After that, we need to give the name of our C file, which is our driver. I'll just say drv.c, if that's what that's called. And we'll just say our assembly file is asm.s. So we give our driver file, and then we give our assembly file after that. And what that's going to do, GCC will look for 32-bit assembly code, and it'll compile it together with the driver file that's been provided to us. And this whole command here will output a file called a.out. And you can notice that if you look in the directory that you compiled this in, you'll notice a new file has been created called a.out. That is going to be the executable file. And so to run this file, we give the command /a.out. And that, doing this within the terminal, that says run the file, or the file after this // is an executable file. And you're telling the operating system to run this file. And for Lab 1, everything's been completed for us. We don't actually have to fill in this assembly stub. However, we do need to run it and note the results. In subsequent labs, we're going to go through this process every time. We're going to take our C driver file. We're either going to type it out manually, or you can copy it from the lab manual. And we're also going to create a separate file, which is our assembly file, or .s file. From this file, you can insert the assembly stub and then fill in the blanks based on the specification file given to us in C. We don't actually want to run or include this specification file anywhere. It's just for our purposes so we can see some C code and then try and more easily convert it into assembly language. Now, after we have successfully completed our files, or our assembly code, we need to submit it. Now, before we submit it, we need to make sure that it's properly commented. Refer to the syllabus to see what is expected of proper comments, but you should have three different components to your comments. There's the program header. This is the part of your comments that appears at the very top of your assembly file. This gives information like your name, the date, the lab number, the purpose of the program, and anything like that. The details are spelled out in the syllabus for you, but it's very important you include this program header. You also have the function header. The function header will appear above every function that we write in assembly. I'll specify before each lab what the functions are going to be, but for this lab you don't really need to worry about that since we haven't gone over what functions are. So for lab 1, you need to make sure you have the program header so far. Another thing that we're going to expect in subsequent labs are the inline comments. The inline comments, they give an overview of what the assembly code is doing line for line. Now, look in the syllabus, like I said, to see what I'm expecting for these, but they do not need to be saying exactly what the assembly instruction is doing. So for example, if we have a move instruction, we don't need to say moving from this location to the next location within our comment. What we're looking for is more of a high-level overview of what you're trying to accomplish. So maybe if you're trying to add a sequence of 10 integers, you could maybe include an inline comment that says grab or fetch the 10 integers and then add them. And so if someone were to look at your assembly code, they could say, ah, yes, you're adding 10 integers here, not you're moving this to here, this to here, this to here, adding this and adding that. That is evident by looking at the assembly instructions themselves. Because assembly is such a low-level language, it's very, very important that you include proper comments within, not only within your lines of code, but also in your program headers and your function headers. Now, once we've completed these components of our program, we're ready to submit it. For submission instructions, refer to the syllabus, but it's very important that you include the proper file name, and you also email it properly. So you need to have the proper subject line in your email. This will ensure that your assignment gets received, and that way I'll know whose is whose. If you don't do these, I may not receive it correctly, or I may have to take off points. So please be sure you have proper comments in all your programs, and you also submit them correctly. If at any time you have any questions about this or what I'm expecting, please email me beforehand, because comments and proper submission is worth 50% of your grade. For Lab 1, I'm not expecting anything but the program header at the top of your file, which again refer to the syllabus for details on how to complete that. But all I'm expecting is your assembly file to be turned in. I don't need your executable file that you've generated. However, I would expect that when I try and compile and run your assembly file myself with the given driver file, that it will work. So if you do not modify the driver file, then and you do your work on a Linux computer, then it should work on my end. If you have any questions about that, let me know beforehand. Thanks.